All right. So, I mean, of course, we wanted to start with a little bit of context, especially for people starting on the mission. I know that many of you might already know most of what I'm going to tell, but I just wanted to have everybody up to speed and at the same level before we start. So this presentation is going to be mostly about a very brief history of gravitational wave detection, some kind of LISA status, and a rough timeline, and a word about how LISA is organized in terms of agencies, consortium, and ground segment, so that I can give you some, let's say, actionable items if you start on LISA, you know, where to subscribe and how to do stuff. That was the main idea. And also, you're going to hear a lot of acronyms, and the idea was to help you with this before starting. So, as I said, history and detections, then a little bit of on LISA itself and the recent developments, how everything is organized, and a little bit of a summary. Okay, well, so let's start with the usual but interesting brief history of gravitational wave detections. But before we dive into the timeline, maybe it's good to remind ourselves why gravitational waves are important and they matter. So for more than Galileo's like 4 centuries, astronomy relied on light, right? From Galileo's telescopes to GWST. And more recently, of course, we've detected neutrinos, cosmic rays, and so on. But all of these traces, all of these trace how matter interacts through electromagnetic or nuclear forces. Gravitational waves are different, right? They carry the imprint on space-time itself, which is generated by massive bodies accelerating. So they let us probe regions that light cannot escape from, like merging black holes, or maybe the very early universe before recombination, things that we can't see with light. So detecting them opens, as you've probably heard before, a new window on the cosmos. And that turns GR, general relativity, into a practical observation tool. That's why building instruments like LIGO, Virgo, and now LISA is so important and transformative. Let's see how this idea, of course first written by Einstein, gradually became an experimental reality today. So the idea of gravitational waves comes straight from GR. So in 1916, just a couple of months after publishing the theory of general relativity, Einstein noticed that this equation, his equation, the field equations, allowed for wave-like solutions when they were linearized. So tiny distortions of the metric that travel at the speed of light. You'll hear a little bit more information about this in the next lecture. But he calculated that accelerating masses, like 2 stars orbiting each other, should emit those waves and therefore lose energy. Einstein was never completely convinced that they were real in a physical sense, meaning that they could be observed. So through the 20s and 30s, he and others debated whether these waves could actually transport energy or whether they were just coordinate artifacts, mathematical stuff. It wasn't until the 50s and the 60s, with work by a couple of names that you've heard before, like Bondi and so on, that the community settled the issue. Gravitational waves are real, and they do carry energy. The challenge, of course, is that they're terribly, terribly weak. They stretch and squeeze the distances by roughly less than 1 part in 10 to the 21, even for the most catastrophic events that the cosmos has to offer. So for decades, they remained a beautiful idea, but something that could not be measured. And yet, some experimentalists, especially in the 60s, decided to try anyway. So you've heard that name before. Is a visionary physicist, Joseph Weber. He decided that gravitational waves were worth chasing experimentally. So he designed a system, an enormous aluminum cylinders actually, many of them here, that was about 2 meters long, suspended with piezoelectric detectors around. And the idea was simple. but quite imaginative, that if a gravitational wave passed through the bar, it would slightly stretch and compress it and excite its resonant mode, much like a tuning fork, for example, responds to a specific tone. So of course it has a narrow sensitive band, but the idea was that if you chose that narrow band wisely, you could maybe measure a gravitational wave. In 1969, he announced that he had detected gravitational waves. So multiple events had been seen in coincidence between different bars located at different places, Maryland and Chicago, mostly. So for a moment, it looked like GR had produced its first direct experimental observation of gravitational waves. But replication attempts quickly failed by others, and even more sensitive bars saw nothing. Maybe we can cite the Italian Explorer Nautilus. The Italian Explorer and Nautilus. They didn't see anything. So likely the signals that Weber saw were due to local noise and fluctuations, statistical fluctuations. Despite that, I think this work created some kind of momentum and at least opened an experimental field. So it brought legitimacy to the idea that gravitational waves could maybe one day be measured. And it also trained the first generation of experimental gravitational wave scientists. In the mid-70s, well before we could detect gravitational waves directly, Hulse and Taylor, what's the name? Russell Hulse and Joseph Taylor discovered something interesting, a binary pulsar system. So 2 neutron stars. 1 neutron star was a precisely timed radio pulsar, meaning that as the two stars orbit each other, Taylor could measure the orbital period very precisely, as you can see in the figure. And they saw that this orbital period was slowly decreasing as the 2 stars were spiraling around each other. When they compared that decay against Einstein's predictions for the energy loss through gravitational waves, the match was perfect, as you can see. And so, within the observational uncertainties, it followed that this GR's curve was a perfect match to their experimental points. This was the first solid proof, though indirect, that gravitational waves existed and carried energy. They received the Nobel Prize in 1993 for this discovery. And of course, that gave enormous credibility to the experimental projects that would later become LIGO and Virgo. This is important to get funding. Okay, so after the bars of Joseph Weber, it became clear that we needed a different type of detector with better sensitivity across a wider frequency range, especially because at that time it was not very clear what kind of sources could be observed. And capable, of course, of measuring smaller strain. In the early 70s, a couple of people produced reports, especially Rainer Weiss at MIT, to try to think about how interferometers could detect gravitational waves. So he studied the different noise sources, seismic, thermal, and so on, and basically concluded that laser interferometry could, in principle, measure gravitational wave strains as small as the 10 to the minus 21 that we've talked before. Around the same time, in Glasgow and Caltech and so on, a couple of other people were following the same idea. You've probably heard of Drever, Kipthorne, and so on. And they basically joined forces to form what became the LIGO collaboration. In Europe, the same thing happened as well, especially between the Italians and the French, and that became the Virgo project. So these interferometers, they use laser beams traveling down perpendicular vacuum tubes, bouncing off mirrors, suspended, just like pendulums, and the passing gravitational waves just change the relative arm length by a very small fraction, yet it shows up in a shift in the interference pattern. This is measured by the photodiode, and this is the base principle for all gravitational wave detectors that we have on ground today. So in the 90s, construction of LIGO and Virgo started, commissioning, learning how these noises behaved, how to tame them, how to mitigate them. The first generation detectors in the 2000s didn't detect anything, but they proved the concept and built the expertise. And then, of course, the area of what we call advanced LIGO and advanced Virgo in the mid-2010s came a reality, and everything was ready for the first detection, which you've heard about in 2015. So this is basically the current detectors. So you have the two LIGOs, Virgo. Geo is kind of a prototype that has not the sensitivity for gravitational waves, but helped a lot for technological development. LIGO India is under construction, and Kagra is also joining the forces right now. So on the morning of September 14th, 2015, both LIGO detectors, Hanford and Washington, as we saw, Hanford, Washington, and Livingston, Louisiana, as we saw before, saw a signal, a chirping signal rising for a fraction of a second above the noise. And when the data were compared, the match was quite good to the templates that we have from GR. And the two signals were time shifted by 6 or 7 milliseconds, which is consistent with the gravitational waves crossing the continent. The source, as analyzed by these templates that I described just before, two black holes, a couple of tens of solar masses, spiraling together, merging into a single 62 solar mass black hole. And the missing 3 solar masses were directly converted to gravitational wave energy radiated. The fun thing is, for a brief instant, this system basically radiated more power than the stars in our observable universe, which is kind of crazy. So this event, named horribly, confirmed Einstein's last major prediction and marked the birth of gravitational wave astronomy as the first direct detection of these gravitational waves. Since then, we've detected dozens of binary black hole merger. In 2017, we observed the first neutron-star collision, GW 170817. That's my birth date, so I know it. And it's quite important because it was accompanied by light across the electromagnetic spectrum that we call a counterpart. And that was also a start of something new, multi-messenger astronomy. As of 2025, the LIGO-Virgo-Kagra collaboration has reported roughly, I think now it's a little bit more, but 100 confident detections. And we now study black hole and neutron star populations statistically, which is another step. This is they call that the stellar graveyard. So these are all the detections by LIGO-Virgo-Kagra. So as you can see, you have the progenitors and the final black holes. The different colors are for the different types. So that's now. So the ground-based detectors, of course, will evolve. They plan some updates. And this is typically 2 big projects that will follow up LIGO, Virgo, and Kagra. There's one in Europe. It's called the Einstein Telescope. I thought I had a slide about it, but maybe not. Yeah, maybe not. Einstein Telescope, which site is still under discussions. It might be in Sardinia, I think, or it might be in Belgium, or maybe in Germany. It's still under decision. And the 2 configurations that people are debating over is a triangle shape underground. I think it's a 10-kilometer arm-length triangle underground, or a double L-shaped configuration. So double L means that you have 2 L's with different arm lengths, which optimizes for 2 different frequency bands. So the goal is to have a broadened sensitivity for these kind of next generation detectors. On the other side of the Atlantic, there's also a big project called Cosmic Explorer, which is more a step-by-step improvement over LIGO. But again, the idea is the same, a 40-kilometer L-shaped detector, which also will be optimized for a broadened band. The cool thing about these next generation things, well, okay, a couple of cool things, is that if you look at the sensitive volume, so the volume in which you could detect, say, black hole binaries or neutron star binaries, it basically covers the entire observable universe, as you can see here. So these are the detections I told you about. So this is the neutron star. This is the first detection. This is the distance, this axis, in terms of redshift. You have the neutron star in blue. These are the binary black holes here. And if you see, so O3, where the before the last observation run of LIGO Virgo, and Cosmic Explorer and Einstein telescopes are in purple and green. So you can see that it basically sees everything, almost everything in the universe. Yes? I think it's Voyager. It's another project. I don't know much about it, actually. Oh, it's a LIGO upgrade. Okay. Yeah. The nice thing is, if you look at a rough timeline, I mean, these are early projects, but they have rough timelines, and they're planned to start constructions around the 2030s-ish, which means probably that they will reach interesting sensitivities around the same time as LISA. And that means that multiband astronomy could be possible with these kind of things, which is super nice. All right, but again, even though they have a broadened baseband, they're very limited at low frequency, right? I think the expected lower bound of these sensitivities for Cosmic Explorer and Einstein telescope is around 2 Hertz. And that is mostly based on, or because of seismic noise. To reach those lower frequencies, we need to go to space. But before that, there is another detection method at very low frequency, and this is pulsar timing. When I say very low frequencies, I mean nanohertz. So gravitational waves that are so slow that the periods are about, years or even decades. And to detect them, we don't use interferometers, but pulsars, so cosmic clocks. And these clocks are these millisecond pulsars, so recycled pulsars. So these neutron stars that are rapidly rotating. And they send us radio pulses with extraordinary regularity. So any passing gravitational waves will slightly distort space-time between Earth and the pulsar. And it means that it will shift ever so slightly the time of arrival of these peaks, maybe by tens of nanoseconds. If we monitor an array of these pulsars across the sky, hence the name, timing array, we can look for patterns, correlation patterns, in these timing deviations. And in 2023, several independent collaborations, there are a couple of names here, I think, Nanograv, EPTA, and so on, look for these correlation patterns, and they all reported evidence for a common spectrum spatially correlated signal, which is consistent with a stochastic background coming from massive black hole binaries, which is also super nice. The correlation patterns corresponds to what's called the Helling-Downs curve, which is a smoking gun, basically, for these gravitational wave backgrounds predicted by GR. So what next in terms of PTA? I think more data, so more time, more data taking, and hopefully start to identify individual sources within that background. And then building, again, these better constraints in terms of galaxy and black hole coevolution / population models when we can study more precisely those backgrounds. When I say backgrounds, it's the spectrum of those backgrounds. All right, so we've seen the very low nanohertz part. We've seen the ground-based kilohertz part. And of course, there's a big hole in there with many interesting sources, as you can see here. And this is where LIGO lies. LISA lies. So in this regime, we're talking about millihertz. So millihertz is waves of periods of minutes to hours. And the, let's say, main sources are the supermassive black holes. When I say supermassive, is millions of solar masses, maybe billions of solar masses, and the millions of galactic binaries in our galaxy. As I told you before, seismic noise makes it impossible to build those kind of detectors on ground, so this is why we go to space. That's why it's a space mission. And LISA, Laser Interferometer Space Antenna, I should have said that before, consists of 3 spacecraft in a gigantic triangular formation. The goal is to monitor, again, by interferometry, the position or the relative velocities of these spacecraft as gravitational waves pass through. Let me just say a quick word about it. I mean, you've seen that before. It's a European Space Agency-led mission with a major participation from NASA. The three spacecrafts will basically follow or trail or lead the Earth. It's still undecided around in its orbit around the Sun. Inside each spacecraft, you will have free-falling test masses, so these kind of cubes floating, which are used as inertial references. So they shouldn't be submitted to any force except gravity, of course. And the test mass separations across the 2.5 million kilometers is monitored by precision laser interferometry. That's the basic principle. The concept is quite new. There are key technologies that have not been tested before. The main one, or one of the main ones, is this drag-free operation, having those test masses floating and the spacecraft adjusting to their positions. And of course, the main goal is to keep those test masses as inertial as possible. Then we need to have precision, and when I say precision, is sub-femtometer precision interferometry in space. So that was a lot of technologies, and there's been this Pathfinder mission between 2015 and 2017 that could fly to validate this technology in space. And good news, the very good news, is that it proved performance beyond the requirements. As you can see, these were the main results, the final results of LISA Pathfinder. These were the Pathfinder requirements. This is the equivalent LISA performance. I don't know if you've seen that kind of plot before. So these are the frequencies. So as you can see, this is the LISA band, right, around the millihertz. This is the sensitivity, so a kind of measure on what kind of strain you can detect. And the final results were the red curve here. So that was a big green light for the LISA mission and its development. And that basically triggered, or that was followed up in January 2025, so quite recently, by the official adoption by ESA. Sorry, this is 24, right, last year. So now let's say the ongoing phase of the mission is the detailed design and manufacturing. That means that prime contractor, industrial contractor, has been selected and starts detailing the designs and building stuff. In the 30s, 32-ish, there's going to be the spacecraft integration and testing. So you bring all the different instruments and parts, you test them. And the nominal launch date is around 2035, maybe 2036, depending on the different orbit options, on an Ariane 6. Of course, that might evolve. But let's say around 2037, 2038, we expect the science operation phase to start. The nominal duration of the mission is 4 years, extendable, if everything goes well, to 10 years. So, exciting, but there's a lot of things to do. That's why you're here. All right, maybe very quickly, I will describe the main sources that we expect in LISA, because that drives the science cases. So this is, again, the expected or target sensitivity for LISA. We'll have an entire lecture on the different noises that come into the recipe on how to build this kind of curves, why there are wiggles here and so on. But let's take it as granted for now. So as you can see, the peak sensitivity is, let's say, around a couple of millihertz, right? And this is where we expect, let's say, the golden sources of LISA, the supermassive black holes. So as I told you before, this is something that haven't been detected yet, because we'll see when they merge. So as you know, galaxies can merge, and we expect the supermassive black holes at the center to eventually merge as well. These supermassive black holes have masses that range to 10 to the 4 to 10 to the 7, maybe 8. Depending on their masses, they have a different profile of frequencies evolving with time. So they enter the band from the left, they merge here, and then they disappear. The event rate is quite uncertain. They're a big error bar. But I think current estimates are about 10 to 100 events per year, which is quite a few. The cool thing is that they have quite large SNR, signal-to-noise ratios. So they really stand out from the noise. You can see them with naked eyes. And it also means that we're sensitive to very high redshifts. Basically the entire observable universe as well, meaning that we would see the first galaxies when the first galaxies formed, right? So that's a very good way to trace the origin and evolution of galaxies in black hole binaries across history. Many scientific questions are attached to it, but you'll have entire astrophysics lectures about them. Things like seeds of these supermassive black holes, because we don't really understand how they can be so big today. How they grow exactly. Is it merging? Is it accreting? And so on. And of course, if we ever detect electromagnetic counterparts, that might tell us a lot about things like their environment. It also has a lot of implications in terms of fundamental physics. We can do tests of GR, especially with the ring down part of it, so the last part after the merger, and also any tests of beyond GR theories. Again, you'll have entire lectures about this. You can see in this plot, it's a very interesting plot. It's usually called waterfall. So you have let's say a representation of the parameter space of these massive black hole binaries. You have the total mass here of your system, and you have the redshift here, and the color indicates the SNR. So as you can see, when you're around million solar masses, you have high SNRs because this color is still, 100 in terms of SNR, and you can go to redshifts of 10 even more. So basically everything. Another type of source are the extreme mass ratio in spirals. So these are a massive black hole binary and a smaller compact object orbiting around it. They're very complicated in terms of physical modeling and waveforms, but they're very interesting because you can observe these kind of massive black hole binary and probe their environments, mostly at the center of galaxies, dense clusters, and so on. So maybe you can extract the mass and spin distributions of these massive black hole binaries and also the physical processes in these closed environments. So MRIs, this is how we call them. Another type of source is these, let's say, multi-band LIGO-type black hole binaries. Of course, we don't see them merging, so stellar mass, right, kind of binaries. We don't see them merging in the LISA band. Most of them will actually never merge within the 10 years of mission of LISA. But maybe, even though the rates are probably quite low, some of them might actually appear in the LISA band and then transition to the LIGO or maybe ET, Cosmic Explorer bands, and merge in them. This is what's called the multiband astronomy. So it's quite interesting because if you can look at the signal way before merger and also complement this observation by what's happening very close or at merger, you can extract a lot of complementary information. Things like spin distributions and so on that might help understand what kind of formation channels are used to form these kind of systems. Yeah, that's it. Yeah, I should move on. And then we have these, what we call these galactic binaries, so compact objects, millions of them in the galaxy or very close to the galaxy, which will emit quasi-continuous monochromatic signals, right? So these are systems that are very far from merger. They orbit each other and lose energy very slowly. And so they will stay in the band for the entire mission of LISA. There are millions of them, so they are superimposed signals, so there's a big challenge in terms of data analysis here. But that can be very interesting because this is an entire population. So we can answer things like how do these kind of systems form and evolve, and how they are distributed in terms of mass, in terms of spatial distribution in the galaxy, and so on. A lot of them will not be resolved individually, so they will form a background. Tens of thousands of them are expected to be, at the end of the mission, resolved. And some of them we actually observe already in electromagnetics, so we know they're going to be there. This is what usually we call verification binaries, these stars. And the goal, in the end, is for all these resolved sources to do maps like this of our galaxy. And of course, on top of all of these sources, there might be other astrophysical backgrounds, so things that we don't resolve individually, but that might just add up incoherently in our signals. Things like PHB populations and maybe an Emery also background. Yeah, that's also possible. There are also backgrounds that might come from the early universe. You're going to have entire lectures about this as well in a cosmology lecture. There are many different processes that can happen in the early universe that might produce gravitational waves. First order phase transitions, cosmic strings, and so on. And we have to be prepared for the unexpected. We might see unforeseen sources. We hope to see unforeseen sources. All right, that was kind of a brief overview of the main science cases. I probably have forgotten some of them, so I apologize if that's the case. But that's the rough, let's say, golden science cases for LISA. OK, so that was the LISA. Now, just a couple quick words about how is LISA organized, especially between agencies, consortium, and the ground segments. I tried to summarize this with a very simple graph, and it's this one. So I have the space segment, right? Building the stuff, launching the stuff. This is, of course, ESA-led, and all the national space agencies, member states, and partners will also contribute to this. Maybe building some parts of the instrument, like optical benches, like test masses, and so on. So at the end of the chain, it's the labs. Amongst you, there might be people working on that, and they will deliver to ESA parts of the instrument. There are also industrial contractors that will also deliver parts of the instrument. And ESA will coordinate everything, and in the end, manage the launch operations. There's also the ground segment part, more on the data collection, analysis, dissemination, and so on. That's also led by ESA. And you have also contributions from the different countries. In Europe, so the ESA member states, the contributions for this science ground segment is gathered in what we call DDPC. DDPC stands for Distributed Data Processing Centers, right? And inside each country, the, let's say, promised contributions to ESA is divided up into the different labs of the country. So many of you are probably part of this DDPC. Of course, on the NASA side, there's also the equivalent, and it's called the NASA Science Ground Segment, which is the contribution to, again, the analysis of the data and so on, the pipelines. But that's also ESA-led at the end of the day. Oops. If you go further down in terms of data flow, you have what's called the LISA science team, which is responsible to coordinate the main science objectives and analysis from the LISA data. And right now, they're starting to organize themselves, but when the data will come, they're responsible to perform the main golden analysis with the data. And they will form what's called science topical panels to answer different questions and write these different papers. But that's not all the science that you can do with LISA, right? This is limited to the basic main use cases of LISA. There's also the scientific community at large, which is organized around the LISA consortium, and that will basically also help dealing with the data, writing papers, and so on. Right, so that's kind of a very personal view, but I think that's a practical view for anyone starting on LISA. So DDPC, so the European ground segment thing, Distributed Data Processing Center, is organized into different what's called coordination units. I'm just mentioning this because you might hear about them, especially if you're involved in DDPC or even the NASA Science ground segment. And these different coordination units that you can see here, I'm sorry about the graph. I took it. It's a terrible graph, but I didn't have the time to redo it. But these different coordination units, they basically represent the different parts of the pipeline. So it starts with what's called the L01, which is like treating, calibrating the data, trying to remove the noise, and so on, which is delivered to L2A, which is the fast pipelines to issue alerts in the hopes that you can turn maybe electromagnetic telescopes to the right place and see electromagnetic counterparts. Then the data goes to L2D, D like deep analysis. These are the long, very complicated pipelines that are trying to extract all the information from the signals, building a list of sources and their parameters. And then these parameter estimation results go to L3C, C like catalog, which will gather, consolidate all this data into a clear, final catalog of sources seen by LISA. And we don't have the instrument yet, but we need to prepare the pipelines. So we need to simulate, to generate some synthetic data from LISA. And that's the goal of this simulation coordination unit. And of course, we need some models, some templates for the signals that we hope to detect in our data. And that is what the coordination unit waveform does. So if you hear L01, L2D, L2A, L3C, that's what it means. Right? Is that somewhat clear? Yeah? Okay. Good. Okay, so that's part of the story. Maybe just a word about the data itself. So the first LISA data release will take place 1 year after the start of the data taking. Data will be public, right? A year after. It will be accompanied by a catalog of sources produced by DDPC and NASA's Science Ground Segment, as we saw before. And the science, before this public release, will be performed by a set of topical panels managed by the LISA science team, as I told you before, right? Following this first data release, there's going to be a new data release every 6 months. So no real proprietary periods, as you can see with other missions. Accompanied, of course, by updated catalogs and so on. No further science interpretation will be done on the data after this first release, right? So once we've published, let's say, the basic papers that constitutes the main science goals for LISA, the data will be offered to the general public, and this is up to the general public to do further science analysis. That's why it's important to gather the broader science community around LISA, and this is what the consortium does, right? So the vision of the consortium, as it's called, is this big bunch of text. I mean, you can read it, but it's a scientific collaboration working together to maximize the scientific return of LISA, handling the LISA data, basically. You can read it, but my view, my take of it is these few key roles. So prepare for science delivery and deliver science beyond what the LST has been doing, LST, LISA Science Team. Provide human resources for LST, because of course LST will say we need a paper about the measurement of the Hubble constant, right? And the people to do this will be experts, and these experts will probably be in the consortium. So that's a pool of expertise. And of course, the consortium is also here to develop and support the community in general. Yes? No roles anymore. Yeah. They're responsible for the basic science questions, and then it's done. It's kind of a, I see it as an insurance for ESA that the basic science will be done correctly as a return of the mission cost. Yeah, of course. Let's say that's the current vision. Something important to know is that the consortium will not have privileged access to the data. So the consortium will work with openly released data as everybody else. So being in the consortium is probably a good idea if you're a PhD student or a postdoc on LISA. And the main question that you have to ask yourselves if you want to be in the consortium is this. Do I want to be a community member, or do I want to be a core member? A community member is a very light thing. It means that you get emails, but you don't have to work on any deliverables. There's no service tracking or anything. And you can choose to get more involved at any time. This is a mailing list. It is. If you decide to be a core member, that requires commitment to one of the working groups of the consortium, meaning that there's a service tracking. At the beginning of each year, you pledge to work on something and deliver something. And at the end of the year, you have to make a statement of what you've been doing. Right? There's a light review system. And if your quota is not reached or you're not interested in this anymore, you can go back to community membership at any time. One of the advantages of being a core member, of course, in addition to working on the data and actively being part of that group, is that you can be part of the decision bodies of the consortium and therefore shape the strategies of the community around LISA. Yeah? Great. Yeah, this is a mic.
It's not super important here, but the LST, the members there have access to the data much before the consortium members were not in the LST.
Yes.
Do they have an embargo, the LST members? Do they have an embargo before publishing their papers because they've seen the data for so much longer than the others, like in LIGO?
Are you asking whether they can publish? So
as soon as it goes public, can they just put out all?
So they cannot publish under their own name, right? They publish under the name of the LST. I think that's what happens.
No, but after the data gets released to public.
Oh no, they don't have any embargoes. I don't think so.
Oh, so they can just publish it instantly. Oh, sorry.
Yeah. So that's all in the discussion right now in the LISA Science Team.
Okay.
So everything up to now is decided by the Science Management Plan, which is vague in parts. The Science Management Plan was what was signed by NASA and ESA and the member states.
Okay.
The LISA Science Team is currently discussing now the details of what is in the Science Management Plan, which has to be kept to, and what wasn't exactly specified. And things like what happens to the LISA Science Team after the scientific panels after that 1 year ends is not discussed at all in the Science Management Plan. There is no discussion about embargoes, which is why Jean-Baptiste is correct in saying there is nothing there. But the LISA Science Team is discussing how that would roll out, because you don't want the case of. Well, the idea is that they want everything ready to go the minute data releases, or maybe before. But if maybe you don't see that source, and they've been playing with the data beforehand, is it fair that they have everything ready to go? But on the other side, they've been working for 5 years, maybe building these pipelines. And and then they got nothing just because nature wasn't harmed. So people are arguing about what is the fairest thing to do with that, but it hasn't been decided.
Yeah, thanks. Hannah is part of the LSG, if you hadn't noticed.
The pledge and statement, it says every year. Is it calendar year or academic year? Because I got very confused when I saw this. When will it be evaluated? December or May or?
To be fair, I think it hasn't really been decided. I mean, so the consortium has been very recently rebooted, as you know, right? So people have registered again to it, made a first pledge. You have to be aware that there's a grace period of 1 year where people are allowed to explore what are the current activities of the different working groups so that they can choose a pledge. What? It's mostly meant for PhD students, but it's not restricted to PhD students as per the rules. And I think the idea is, so it's been rebooted a couple of months ago. There's been the first pledges. I think the idea is next year around the same time, there will be a rough review. And at that time, I think we will strictly enforce the pledging and service tracking thing. Yes?
How big is the LSD? How many people?
20.
20.
So they were picked by
Nora.
6 were picked by NASA, and 6 were picked by NASA, 11 were picked by European Space Agency. 1 is consortium representative, which is selected by vote of the LISA consortium. And then 2 further people were later added on as complementary scientists, also by the European Space Agency. So you have 13 selected by ESA, 6 by NASA, and 1 by the LISA consortium. And then the NASA and ESA project scientists are team meetings are chaired by them.
And if I understood correctly, only the 4 members in the consortium vote for this kind of thing.
Yes. That's correct. But again, the consortium only sends 1 representative to the LSD. Right? The rest is managed by the agencies themselves.
And that's coming.
Yes. Okay, I think that might answer a little bit how the consortium works in terms of decision bodies. So the main decision body is the consortium council, which basically gather the working group chairs and representatives, the member groups, because you can register as a member in a group, probably your institution, and the persons who are elected, so the spokesperson and the LSC representative that we just mentioned. Then you have the executive body, or bodies. The main one is the management team, and you have a bunch of committees to advise the council and the member teams, the management team. So committees are things like diversities, inclusion, and so on. What are the other appointment committee, and so on. So supporting teams, basically. And then you have the working groups who really carry out or manage the carrying out of the scientific and other work of the consortium. I've put a list of the current science working groups. So you have astrophysics, cosmology, data analysis, fundamental physics, instrument simulation and processing, instrumentation, waveform. So as you can see, that matches roughly the lectures that you'll have here. But you also have other working groups, and efforts work in these other working groups are also recognized as work when you do your commitments. Things like communications or early career scientist support group. Yes? Yeah.
Yeah, as a young PhD / young postdoc, can you join if your supervisor is not in any of these working groups?
The answer is yes. It's an individual registration system.
Okay.
You still have to make sure that if you register as a core member, that means that you will have a commitment in terms of work. So, of course, that has to be validated. But you don't register in a group automatically.
Okay.
You can have individual
If I remember correctly, you did have to find, if you were a PhD student, have somebody at least supervising you from within the.
You need to validate your.
Okay.
But
Yeah.
postdoc, no.
No, postdocs you can just.
Okay, good to know. I didn't remember that.
But it doesn't have to be your actual thesis supervisor. It can just be somebody you would be working with. So
I see.
that's
Okay.
as far as I understood the rules. I mean.
All right, that's quite a bit of information already, and it's almost time, so I'll wrap up this presentation with some generalities again. From Einstein to function network of gravitational wave detectors in a century, this is a great time, I think, to be a scientist right now. Gravitational physics is a new, vibrant field. You've probably noticed. That's why many of you are here probably today. Many exciting prospects. I'm not even talking about LISA, but in general, different types of detection, detectors, science opening. Important synergies between the different detectors or even beyond gravitational waves. So please stay aware of everything that's happening in the broader sense of the term. And also, a last thing, LISA is a big mission. It's a complicated, big mission, and so it's a global collaborative effort. That's why we wanted to also build this, this school. You'll be the ones to handle the LISA data. And there are many challenges still, many questions open. So, yeah, the success relies on you guys. More practically, join the consortium if you want to. It's open to anyone. Participate to working packages if you're a core member. You can sign up via this URL. If you want to play with the data, there are available past LISA data challenges, so mock data that you can use. You can check out this website for existing data sets. DDPC is working to produce new data sets. I think the plan, to be confirmed, but the plan is to release them openly to the broader community as well. So kind of a handover to the LISA consortium. So you might also soon be playing with this kind of data. And also build your network and start collaborations. And that's it. Do you have any questions? No, I think that was OK, very good. Let me just stop the recording.